Okay, so let's start with lecture 5, Intel RSS. So I put it here because it's really part of the planning stage. It defines some rules for the planner. So what is safety? Should the AV try to avoid collisions at all cost? Should it be statistically better than a human driver? Or should we follow the best practices in systems engineering, like we discussed the ISO 26262 standard before? Or we just follow the rules of the road? So absolute safety is impossible. For example, in the scenario below, the AV, the yellow car in the middle, in the center lane, can do nothing to ensure absolute safety. If the red car swerves into the AV, collision cannot be avoided. So to avoid this scenario, should the AV never drive in the center lane, or should it never leave the garage? So neither is a useful option. So avoiding collisions at all costs leads to a useless system. How about statistics? So statistically better than normal drivers, human drivers. So one problem is that it's infeasible in practice. So in the United States, about 40,000 people are killed per year in traffic accidents, corresponding to a probability of 10 to the minus 6 of a fatal accident per hour by human drivers. So if we want AVs to be 100 times safer than human drivers, so we want AVs to kill 400 people per year, then we need P is roughly equal to 10 to the minus 9. So there's a theorem proved in the paper to make sure that probability of an accident per hour is at most P. One must drive more than 1 over P hours after every software update. So which 10 to the minus 10 to the 9 hours is 40 million days. So we'll try to tell that to Tesla, which issues frequent over-the-air software updates. So you may say we can do simulation hours instead of actual on-the-road hours. But simulation cannot replace real-world testing. Simulation fidelity is limited and the scenarios are limited. So that's infeasibility. Another is that it's not transparent. So what will happen when an AV is involved in an accident? So will society be satisfied with a statistical argument? So you may say to the victim's relative that we're sorry that our AV killed your only child, but statistically it's 100 times safer than human drivers. So one of the 400 people killed every year by AVs, you're just unlucky. That's not a good argument. So follow the best practices. So you may say we did all other players did and more. We got the best sensors, redundancy, verification, validation, miles-driven, simulation time. So the problem is that there's no guarantees. Just because you tried very hard doesn't mean that your car is guaranteed to be safe, and leads to over-engineering. And it's not transparent. What will happen in case of an accident? So follow the rules of the road, even if the AV strictly follows the rules. Others around it may not do the same. So for example, if a car runs a stop sign at high speed, the AV should yield to it even if the AV had right of way. So we saw in the introduction lecture, the Uber vehicle that ran down a pedestrian, the pedestrian was crossing the highway. So obviously Uber vehicle is respecting the rules of the road, but that's not enough. The vehicle must be safe and based on current driving scenario. So rules of traffic, there are hard rules which set limits on vehicle operation. For example, come to a complete stop at red lights. Don't cross a double yellow line. Obey posted speed limits and yield to other road users when signaled. So these signals can be programmed into the AV. It's very easy to program these rules with a software program. But the difficult part is the implicit traffic rules, a set of principles applied by the human driver. They are flexible and culturally dependent. For example, keep a safe distance from the car in front of you. How long is a safe distance? Drive cautiously under limited visibility. Don't drive slowly in the fast lane. Don't cut off other drivers. So all these rules you may find in your training manual when you are testing for a driver's license. They're written, but they are informal. They're implicit. They cannot be formalized with a C code. So the question is how to formalize and program these rules into the AV. So Intel Mobileye, which Mobileye is a company in Israel acquired by Intel. So they proposed RSS, responsibility sensitive safety, in 2017, an open, transparent, and technology neutral starting point for the industry to align on what it means for an AV to drive safely. It's described in this article in 2017. So it formalizes human notions of safe driving into a verifiable model with logically provable rules, defines appropriate responses, and ensures that only safe decisions are made by the AV, and clearly assigns blame or responsibility in case of accidents. So it's okay for an AV to be involved in an accident as long as it's not responsible for causing the accident. So that's the philosophy behind it. That's why it's called responsibility sensitive safety. So the goal is that an AV should never be responsible for accidents, meaning that first, it should never cause accidents. Second, it should properly respond to mistakes of other drivers. So it's a mathematical interpretable model formalizing the implicit rules of what's a dangerous situation, what's the proper response to a dangerous situation, who's responsible for an accident. It provides a check on AV decision making and the performance benchmark for regulators. So we set the rules of the game in advance and not after an accident. So let's watch a video.
I don't think the sound is coming out on Zoom.
Okay, I need to turn on the sound. Sorry.
Thanks. No worries.
Everyone agrees that autonomous vehicles are the future of mobility. But how can we be assured of their safety? Although we don't consciously think about it, humans follow a few basic principles to help us drive safely. For example, always maintain a sufficient distance from the vehicle ahead of you, or the right of way is given and not taken. However, these principles are subjective and open to interpretation. To provide true safety assurance for autonomous vehicle decision-making, we must first clearly define those principles. Only then will we be able to program an autonomous vehicle that will be smart enough to negotiate the road alongside unpredictable human drivers. In order to formalize human common sense, Mobileye has developed the Responsibility-Sensitive Safety Model. RSS is an open and transparent model that uses mathematical formulas for safe decision-making by defining what constitutes a dangerous situation, what caused it, and the proper response to the dangerous situation. By doing so, we can ensure that the autonomous vehicle will not initiate a dangerous situation, and also ensure that it responds appropriately when a dangerous situation is forced upon it by others. For example, while merging into traffic, the autonomous vehicles will cut in only with a minimal safe distance as defined by RSS. RSS builds upon these simple definitions of a dangerous situation by incorporating more complicated scenarios, such as junctions, limited sensing scenarios, and even unstructured roads. This allows us to gain full coverage of all possible scenarios in a multi-agent environment and clarify responsibility for collisions involving automated vehicles in the real world. These are just a few examples of how RSS is designed to mimic human judgment using mathematical definitions. At Mobileye, we believe that the challenge of providing verifiable safety assurance of automated vehicles is one the entire ecosystem must solve together. Therefore, we invite industry players and regulators to engage with RSS as a starting point for finding a true safety guarantee for autonomous vehicles. Join us in our journey to make safe autonomous driving a reality. Mobileye.
So RSS focuses on the safety of the planning module in the pipeline of sensing, planning, decision-making, and control. So it fits here. So it's arguably the most difficult part as it involves negotiating with other road users in a closed loop online manner. So 5 rules. Number 1, do not hit the car in front with safe longitudinal distance. So here's the front car. Here's the Eagle vehicle, the rear car, and so the distance from here to here is safe. It's far away, but as you get closer and closer, at this point, it's unsafe. It's too close. So you should brake to restore a safe longitudinal distance. Based on the rule defined by RSS, which gives you an exact number of the safe longitudinal distance. Number 2 is a lateral distance. So do not cut in recklessly. Number 3, a right of way is given, not taken. So number 4, be careful in areas with limited visibility. Number 5, if you can avoid a crash without causing another, you must okay, make it smaller. You must. Oh, okay, that's it. Okay, so criteria for a good formal model. One is soundness. When the model says that the AV is not responsible for an accident, it should clearly match common sense of human judgment. On its usefulness, it's possible for it to efficiently create a driving policy that guarantees to never cause accidents while still maintaining normal flow of traffic. Don't avoid collisions at all costs and stay in the garage. So it's possible, especially for early versions of Google self-driving car, it's too conservative. So it observes all the traffic rules and drives under the speed limit, but it causes disruption to normal traffic because normal people drive faster than speed limit. So the safe option is to go with the traffic, not to blindly obey the rules. So can we ensure that a driving policy based on RSS does not lead to accidents of our blame? So it's not trivial due to butterfly effects, where a small action leads to a chain of events that lead to an accident. So the system should prevent such butterfly effects. But it's possible using mathematical induction, we can construct an efficient procedure for guaranteeing RSS. So high-level description, you define high-level, you define safe distance. For example, longitudinal. A situation is dangerous if it's non-safe longitudinally. Blame time, the first moment in which the situation becomes dangerous. Proper response, if the longitudinal distance becomes non-safe, brake longitudinally. Responsibility, we prove that a collision can only occur if one of the agents did not respond properly. So the responsibility is on the agents that did not respond properly. So for the lateral maneuver, so for example, here, the Eagle vehicle is the yellow, and red is the other vehicle. So the proper, so if the red is violating the safe lateral distance by moving sideways like this, then it's blame time. So at this point, a blame has been placed on the red vehicle. So, and then the red vehicle should, according to RSS, take a proper response to steer back in the right direction. So brake laterally, it doesn't really make sense, but in this particular context, it means a brake while steering to the right direction. So in this case, the two vehicles, the red perhaps is trying to change lanes. So it turns in this to the left, but the distance is too short. So these boxes indicate safe distances. So it's this is the blame time. At this point, the red is to be blamed. And then the proper response is that the red should brake laterally, that is turning in the right direction, and the yellow should brake longitudinally, slow down in a mild way. So since red is cutting into yellow's lane, so in this case, the blame is on the red vehicle, but the yellow vehicle still has to make a response to keep safe. So both cars must respond, make a proper response in this scenario. So a non-safe longitudinal maneuver. So here's the two cars. So it's getting too close. At this point, the yellow means the safe region, lateral and longitudinal, is the box here. This region is intersecting with the red car, so it's unsafe. This is the blame time, and then the yellow should brake and to allow red to change lanes. For this case, non-safe longitudinal maneuver oncoming. So yellow is going north, red is going south, and there's intersection among their lateral dimensions. So at this point, red should brake hard, and yellow should brake mildly, since red is cutting into yellow's lane in the oncoming direction. Maybe it's trying to pass another vehicle.
Yeah, I had a question on that one.
Sure.
Suppose the red is passing another vehicle, then it cannot kind of brake because it cannot go back.
Well, you can abort, right? You can stop passing.
Yeah,
Yeah.
but that might not be possible.
Yeah, sometimes it's not. Yeah.
Yeah, there could be a queue behind the truck or lorry or something.
Yeah. Okay.
Yeah, I just how you drive in practice, you try to increase the speed instead to make it before collision or something. You should never take it over in the first place.
Yeah, but this may happen due to limited visibility, due to fog, due to a curve or something. So this may happen.
Or heavy traffic.
Yes. So responsibility assignment, blame assignment. So if it's a red car hits the yellow car from behind, then yellow is not responsible for the accident. If it's a side hit and red is traveling in its own lane and yellow hits it, then red is not responsible. So that's consistent with your intuition as a driver. And that's important because RSS is designed to be intuitive and used in a court of law to assign blame if an AV is involved in an accident.
Well, suppose in the previous slide, it's so difficult because suppose the red car in the previous slide. Oh, sorry. Yeah.
This one?
This one, yes. So hit from behind, suppose the red car has some failure on the engine or something, and it cannot stop. Then the yellow should accelerate or turn or something to avoid collision. Or?
That's a very good point because in the following slides, I will show the prerequisite of these rules is that you have a range on the acceleration. Yes.
Yeah, maybe the red driver is sleeping or something. Yeah.
Then that's clearly a responsibility. Yeah. No matter what the cause is, could be red car has a malfunction, could be the driver is not attentive. Whatever the cause is, the blame is on the red car.
Yeah, but the yellow could maybe avoid this collision.
Yes, but the yellow has an assumption, which I'll discuss next, on the other vehicles.
Yeah.
Yeah. So safe distance. The AV, this AV should keep safe longitudinal and lateral distance, longitudinal and lateral, from other cars. So if the front car slams on the brakes hard, maybe due to something jumped into the road, then how much longitudinal distance does it need to avoid a rear end collision. So, and for lateral movement, if the left or right car suddenly swerves, how much lateral distance does it need to avoid a side collision? So here's the definition of safe longitudinal distance. Consider two cars traveling in the same direction, front car CF and rear car CR. In order to ensure that CR never hit CF from behind, it's the responsibility of CR to keep a safe longitudinal distance dmin from CF, which should be large enough so that CR will not hit CF. So to define this equation, we need to consider the worst case situation. CF will suddenly brake hard and it will cause CR some response time rho. Could be a human response time, or for AV could be sensing and reaction delay in the computer system. To figure this out and to start braking as well. And then both cars will decelerate, assuming known parameters of rho max, the maximum deceleration rate due to braking for CF, and rho min, the minimum deceleration rate for CR, alpha max, maximum acceleration rate for CR. We can derive dmin as this formula. So here's the derivation. So I drew 3 graphs. One is position as a function of time. Red is the front car, and black is the rear car. And this is velocity, and this is acceleration. So this shows the worst case scenario where the front car brakes hard with alpha. Alpha max is the maximum acceleration rate. So the front car suddenly brakes, and the rear car initially is accelerating in this response time. So I think I didn't draw this very accurately. The front car brakes for starting from time 0. So, and then the velocity of the front car will decrease rapidly with rho max as the slope. And the rear car within the rho response time is still accelerating with alpha max. But after it realized that the front car is braking, after rho, it will decelerate with rho min. So initial distance is d0. That's the we want to figure out the minimum d0 to avoid accident. At time 0, front car has velocity vf, and rear car has velocity vr. So front car starts to apply brake and travel the distance of this before stopping. So you can derive this equation with average speed and time to stop, similar to what we discussed before. And time rho, the rear car reaches the speed of this, VR plus rho alpha max, and travels a distance of average speed times time. And time rho, rear car starts to apply brake with constant deceleration rho min and travel the distance of this. So for two cars to collide when both come to a full stop, so the smallest worst case distance between them will happen either at time 0 or when both come to a full stop. So when they collide, when both cars come to a full stop, the minimum d0, that's dmin, must satisfy this equation here. So that's the distance traveled by the rear car, and that's the no, this is the rear car travel distance. Rho mean. Oh, this is the rear car travel distance before time rho, and this is distance after time rho, and this is the distance traveled by the front car. So the difference between them is the rho min, the minimum distance, d min, to ensure that the two cars would not collide. So the distance, that's the difference between these two vehicles, will gradually decrease until in the worst case, until this point, when both cars come to a full stop. So the figure on the right shows the threshold situation where the two cars just touch each other when they come to a full stop. So this defines the d min. Any distance longer than d min is safe. Okay, any questions on the derivation?
I'm just wondering how you would obtain these maximum and minimum values. Like surely they will depend on like if there's a slope in the road, or if it's slippery, if it's ice, or if it's bare.
That's a very good question. So that's similar to what Carla asked. So
Okay.
let me skip this one. Yeah. So RSS allows to formally define the desired balance of safety and efficiency of AVs on the road. So if we assume a large deceleration rate rho max for the front car has a very good brake, then d min should be larger to be safe. Or if the larger acceleration rate alpha max or smaller deceleration rate for the rear car has a bad brake, then also d min should be larger. So in either of these cases, the AV will drive more conservatively, resulting in lower efficiency, and vice versa. So AV's behavior, the d min, is determined by the parameters alpha max, beta min, and beta max.
Okay.
And these parameters should be determined by regulatory authorities working with car makers. In the United States, it's the National Highway Traffic Safety Administration. So obviously, every car has a different set of parameters. And if the AV goes on the road, it has to make some assumptions. Exactly what will be the parameters, especially the AV knows its own performance. So AV knows alpha max and beta min for its own car. That's no problem. The problem is beta max. So how hard can the front car brake? If the front car has a perfect brake and just stops instantly, then the rear car will have to keep a long distance. And that's not realistic if you make that pessimistic assumption. So to be realistic, you must assume a beta max for the other cars around you. Exactly how to determine that is based on regulatory rules. So if regulatory authority gives this beta max for all cars on the road, then car makers should respect that beta max and don't make their brake so good, right? And then given its beta max, and all the AVs can make decisions of d min and keep safe.
I had a comment also. In Sweden, we have a rule about a 3-second distance. So how is this related? This is a distance in meters. In Sweden, we have seconds.
So this is distance. So if you look at the figure here, so what we are trying to find is the d min is the initial distance to avoid collision at the end. And then how do you map that to time? So this is time to collision time. So this should be 3 seconds.
Well, for a human driver, it's much easier to count 1, 2, 3 than to kind of estimate 400 meters or whatever it's needed.
So if you look at the formula, besides the alpha beta parameters, it's also dependent on VR and VF, the front car and rear car velocities. So these combined with accelerations determine the time t. So the time t is implicitly defined in here.
Yeah, but the idea here is that the time is kind of more or less constant. So 3 seconds works for many different speeds. But maybe it's not true.
Well, the reason they define it in terms of distance is for implementation in the planning module of an AV, the distance can be determined by radar easily. So it's implementable in the planning module. If it's time, it's harder because it's not a constant motion. You have acceleration, deceleration. So the time is a derived parameter. It's not a measurable quantity that can be used in the planning module.
So for humans, they notice that a car pass a traffic sign or something, and then you can count how long time it takes before yourself pass the same object. But that is more difficult, I guess, for autonomous vehicle.
Time is reasonable but not formal because if you can derive the time from these equations, it's not a simple formula, and the 3-second rule is a heuristic. It's not a guarantee, like in this RSS formula. Yeah. If you had a constant traveling speed of both vehicles, you can derive a time to collision based on constant speed assumption, but the speeds are not constant. And the time is a complex nonlinear function compared to the distance. Yeah. And also to estimate time, you need to actually perform some calculations. Whereas for distance, you can read it out from the radar. So if you read the paper, it has a slightly different notation. Alpha max acceleration is alpha max, alpha min brake is the beta min, and so on. So just in case you read it, I know you won't. So proper response. So in case the distance between the two cars becomes less than the min, then the AV should perform a response. After response, apply braking of beta min until a safe following distance is restored, or until the vehicle comes to a complete stop. So RSS can be a proactive safety mechanism that improves the automatic emergency braking. So it's called automatic preventive braking to determine the moment when a vehicle enters a dangerous situation, then use the comfortable subtle braking beta min to help return the vehicle to a safer position without waiting for an imminent collision to engage maximum braking force. So this preventive approach would provide a stopping distance buffer that could prevent a chain reaction of braking and swerving should an emergency stops occur. So notice that in the formula, the rear car only applies the beta min brake, not the beta max, because this rule is really for preventive measures, not for emergency measures. So the lateral distance enables AV to be aware when their lateral safety may be compromised by unsafe drivers turning into their lanes. So here's the formula, dmin laterally, and here's the derivation. Yeah, so at time rho, again, the reaction time before the rear car takes action. So has a lateral speed, left car has a lateral speed, rear car, right car reaches a lateral speed of this. That's the worst case. And left car travels the distance of average speed times rho. Right car travels the distance of its average speed times rho. And both cars start to decelerate laterally, and each travel distance in order for the final lateral distance between them to be at least mu, the maximum initial distance, dmin, is the lateral distance, is the safety margin. So so that if both moves slightly to the right by mu, it's still safe. If left car moves slightly to the right, it's a margin of error. Mu plus the this formula here, the this measures the final distance between them after they perform lateral braking. So here's the proof in the paper. Again, notations are slightly different, and there's a typo here. Should be plus sign, not minus. So rule number 3 is right away is given, not taken. So on well-marked roads, right away is clear. Lane lines, signs, and traffic lights establish priorities for routes as they intersect one another. But there are other times the right of way is less clear, and human drivers must negotiate with one another. For AVs, this negotiation must be formalized so that machines can make that same negotiation and be sure to arrive at the same conclusion. So if a stop sign exists, drivers are expected to give the right of way to vehicles without a stop sign. So that's a vehicle traveling in the direction without a stop sign. So sometimes they don't. So if a car ran the stop sign and created the dangerous situation, AV must still respond accordingly. So it has right of way on paper, but should not let a crash happen just because the rules give it the right of way. So it's the same as what's written in your driver's manual. So rule number 4, be cautious in the areas with limited visibility. So many factors can affect visibility while driving. Aside from the weather, factors such as road topography, buildings, even other cars can obstruct views of the road and of other road users. Depending on the surroundings, humans naturally put bounds on their behavior to avoid unforeseen dangers. So on a major thoroughfare, it's not reasonable to expect that pedestrians will suddenly jump into the road. However, on a street near a school or neighborhood, it's much more likely. And for drivers, it's responsible to expect pedestrians to suddenly step into the road. Drivers must proceed cautiously, especially as they approach crosswalks or pass cars parked along the street. So here, the pedestrian is not visible to the driver, to the vehicle. So the vehicle must proceed cautiously. So occluded car scenario. So here's a scenario where the rear car CR is at a non-safe distance with regard to a occluded car, blue car. So here's the blue car. It's perhaps broken down on the road, and red car is traveling fast. So the distance from CR to CF, this distance is unsafe based on the formula dmin we saw before. I'm sorry, satisfies the dmin. So distance is satisfied. Oh, okay. I think it's marked wrong here. So the blue car CF, blue car is stopped or very slow. So the distance from CR to CF may not satisfy demand based on its speed. So yellow car cannot see blue car because of occlusion by the red car. So if the red car suddenly swerves to avoid collision with the blue car, yellow car may not have enough time to avoid collision with blue car. So that is the distance from yellow to blue is unsafe. It's less than dmin. But the yellow car cannot see the blue car, so it cannot detect it. So assume the worst case, unless the existence of a car in a certain kinematic position is unreasonable, which is formally defined. So assume the worst case. So in this case, the occluded blue car is very slow or stopped. It's an unreasonable assumption, unreasonable situation. So yellow car will not be responsible for causing the accident. If the red car swerves and yellow car hits the blue car, the yellow car is not responsible. So if you didn't have this assumption, if you didn't have the unreasonable assumption, the yellow car will have to keep a very large longitudinal distance from the front car, which will make rule 1 useless. So you never know what's in front of the front red car. So if you make the pessimistic assumption that that may be a parked vehicle, then the dmin must be very large, which is not makes the driving behavior very conservative. So the red car, on the other hand, can see the blue car and should either keep longitudinal distance dmin or change lanes according to RSS. It should never suddenly swerve to avoid a collision. So distance from CR may not satisfy. Yeah, I think I didn't explain it too well, but the figure is right. So yellow to red is safe. The dmin is satisfied. And yellow to blue is unsafe. Dmin is not satisfied because blue car has a very low speed or parked. And red to blue is unsafe. And if the red car suddenly swerves and yellow car hits the blue car, then the yellow car, the robotic AV, is not responsible because of this because of the assumption. So rule number 5, rule number 1 and 4 create formal definitions to identify what a dangerous situation is and the proper response for the AV. So number 5 covers scenarios where a dangerous situation may have been imposed. So suddenly that a collision cannot be avoided unless a more evasive action is taken. So it says that if the AV can safely and legally avoid a crash without causing another one, it must do so. So here, if a front car suddenly swerves into the next lane, exposing an object in the road, the following car's time of exposure to this object is insufficient to stop in time. However, if the next lane is free, the following car can follow the front car and take evasive action to avoid the accident. So I think this line belongs to the previous slide. Okay, but this picture shows another scenario where some boxes fall off the front car, and the rear car should swerve to avoid a collision. So if the AV can avoid a crash without causing another one, it must do so. So RSS is open source, and as a C++ library, it has been integrated into Baidu's Apollo planner module. So this is Baidu's planner module with different driving scenarios. So this is the mission. This is the planning for different scenarios: default, side path, stop sign, and so on. So in the planner, there's a new software routine for RSS checking, RSS decision making. From the role environment from sensors, the RSS decider checks and decides if the current situation is dangerous or not, and takes necessary actions, a proper response if dangerous. And it's integrated into the driving simulator Carla. So it uses the library to evaluate if a driving situation is safe or unsafe. So here's a video. So here let me see the so they add RSS sensor to Carla. It's a virtual kind of sensor. So sensor evaluates longitudinal and lateral conflicts. It does not yet cover intersection conflicts. So green is safe, yellow is only lateral or longitudinal unsafe. Red indicates a dangerous situation that requires a countermeasure according to RSS. So here's the current to the front car is green, which is safe, and then it becomes unsafe. So at this point, these are safe. So okay, the center bar, the center green is the longitudinal state. It's safe. The yellow on the sides are the lateral states, which is laterally unsafe. That is, longitudinally it satisfies demand from the front car, so it's safe. But laterally they are in the same lane, so laterally they're unsafe. So now it's unsafe according to RSS, the red. Oh, okay. So I didn't explain it very well. So the Eagle vehicle is behind this this car. So so right now, I'm not sure. This is the Eagle vehicle. I think so. Oh, okay, it is the ego vehicle. And yeah, so the point is that, you know, you can determine the safe distances and take any proper responses if a dangerous situation occurs. And safety verification. So safety. So here's the NHTSA pre-crash scenario typology for different scenarios: running red lights, running stop sign, and so on. So they cover 99% of 6 million crash scenarios, and RSS covers all these scenarios. And it agrees with human judgment. So safety verification by induction. So if any driving policy that complies with RSS proper response is guaranteed to never be responsible for accidents. So proof start of the induction. Suppose we start at a non-dangerous situation because we start at a full stop and perform induction. So if the next time step is still non-dangerous, we're done. If not, then TB is a blame time. If the situation at TB was not dangerous, and since by the constraints on the policy we were performing, the proper response during the TBT interval, then either there's no collision or it's not of our responsibility. So interesting issue is ethical issues. So recall from Rule 5, if the vehicle can avoid a crash without causing another one, it must. So it doesn't address the trolley problem we discussed before, which requires the AV to cause another accident in order to avoid one accident. So for example here, you have two choices: run down a jaywalker, it's not your fault, or run down a pedestrian on the sidewalk, but it is your fault. So under RSS, the AV will always choose A and never choose B. Unless it's certain that P is 0, it'll never kill the pedestrian. If P is non-zero, no matter how small, it'll never choose B, because choosing B means that you kill a pedestrian on the sidewalk. So, choosing A means that you kill the pedestrian that's crossing jaywalking. So according to the rule, if it can avoid a crash without causing another one, it must. But in this case, you're avoiding a crash while causing another one, so it shouldn't. So, but this scenario is pretty artificial and not realistic. A question?
Yeah, it's like many good drivers avoid accidents when other vehicles make mistakes. So to cover up for other mistakes, other drivers or vehicles' mistakes is not shown in this rules.
No, it is shown. Is talked about in the in this rule. That is rule of right of way is given, not taken. So even if a car runs the stop sign, so the AV should still yield. So it's not shown in the lateral speed, lateral distance, and longitudinal distance rule, but in the other rules, which I did not discuss in detail, they do formalize the notion of right away is given, not taken. So for this particular scenario, if there's no jaywalker, I'm sorry, if
there's no pedestrian on the sidewalk.
No pedestrian on the sidewalk, yes, or if P is 0, then it will choose B. But if there's any possibility of causing another accident, then the AV, according to RSS, will not choose B. but of course, the rule is just so RSS is currently being standardized as an industry standard. So the idea is that if everyone follows RSS, then it's easy to assign blame. So it's not saying that RSS can prevent all accidents. No, accidents will happen. What RSS helps you to do is to assign blame to the accidents.
But in this case, suppose there are like 5 jaywalkers, but only 1 pedestrian, it would still kill the 5?
Yes. So that's according to the rule. Of course, the rule can be modified to, as said here, maybe extended to address ethical issues, but not in the current version.
It was also a bit. I was thinking about that. It had to be able to do this maneuver safely, but also legally. Like, say for example, if it's about to hit a jaywalker, and it could cross a double yellow line, which is illegal, but it could do it to avoid a collision. Wouldn't that be a better option to break the
Obviously,
than kill a human?
for crossing a double yellow line, that's obviously okay with the rule, because the rule says if the vehicle can avoid a crash without causing another one. It doesn't say without violating other rules. Violating other rules is okay.
In the previous slide, it said like it had to do it both safely and legally, I think. Like a couple of slides ago. Or maybe I think so, at least.
Legal. Did it say that? Oh, safely and legally avoid a crash. So any violation of traffic lights or lane markings or any such traffic rule violations, as long as it doesn't cause a crash, it's okay. Legally avoid a crash. Yeah, you can interpret it in a narrow sense. Crossing a double yellow line, is that legal? Well, I guess the legal here is looser. So these minor traffic violations should be okay.
Okay.
So interesting argument between the mortal enemies, NVIDIA and Mobileye. So NVIDIA proposed something called safety force field in 2019. So it's a robust driving policy that analyzes and predicts the vehicle's environment. It determines a set of acceptable actions to protect the vehicle and as well as others on the road. So these actions won't create, escalate, or contribute to an unsafe situation, and include the measures necessary to mitigate harmful scenarios. So there's a marketing video for it. And then just as NVIDIA came out with SFF, Mobileye CEO wrote a blog openly mocking NVIDIA, pointing out innumerable similarities to RSS, which is proposed in 2017. Despite uncanny similarities, NVIDIA's SFF fails to match Mobileye's RSS. And then they have a long document enumerating all the similarities, which shows that SFF is a close replica of RSS. So summary, so RSS formalizes what is dangerous, what is the proper response to danger, and who's responsible for accidents. So soundness is that it complies with the common sense of human judgment, and usefulness is that we give 100% guarantees to never cause accidents. We didn't say never be involved in accidents. We say never cause accidents, and always properly respond to dangerous situations. Let's just spend a few minutes watching this video to see if it's similar to RSS.
We all would like a vehicle that monitors the surroundings and shields us from collisions. The safety force field is a practical realization of that. It's not possible to guarantee safety regardless of what other actors in traffic do, but it is possible to guarantee that we do not contribute to an unsafe situation. If all actors in traffic had that sort of guarantee, then no unsafe situations or collisions would occur. The safety force field takes the vehicle's understanding of the surroundings and determines a set of acceptable actions. To do this, it uses a constructive computation to consider which actions are helpful in maintaining obstacle collision safety. The acceptable actions never create or escalate an unsafe situation. And this computation can be combined with any software for autonomous driving as a layer in the motion planning that monitors and protects against unacceptable actions. The safety force field follows from one core principle as opposed to a large set of rules and exceptions. So the beauty of the safety force field or a provable planner of this type is that the guarantees that it provides have been mathematically proven, and it seamlessly can handle highway driving, cluttered urban scenarios, and even unstructured parking lot type of driving. It also separates cleanly obstacle avoidance safety from a long tail of rules of the road. The real world is a very complex place, and we have to understand that ideally it would be there as a sort of veto power on anything unsafe that would occur. And the motion planning and other things that would operate on top, or even a human driver, if you had this underneath, would do the normal everyday driving. And if you did brush up against an unsafe situation, then it would push you in the right direction and keep you safe. It considers longitudinal and lateral constraints together, and the constraints can also be visualized in a very direct way. It's a beautiful thing that we have Drive Sim to our disposal at NVIDIA, where it's in the nature of something like the safety force field that the situations we want to test it in are inherently very dangerous, and we could do that in Drive Sim without putting anybody in harm's way.
So I don't know about you, but I didn't see any difference. Just like RSS.
But what about practical issues? For instance, if you stay for a red light and then it becomes green, in some countries, every car starts simultaneously. So if you stay and wait for the first car, you will be collided. The car behind you might think that you are going to run, but you don't.
No, but that's covered in this safe longitudinal distance scenario. So we have this formula here. So if a vehicle behind you hits you, then it must be violating this formula.
Yeah, sure. So, but the human driver might think that you are going to start because it's green light, but you are waiting for this distance to the car in front of you.
But the light color is not a factor in the formula. So the formula is very strict. So it only has the velocities, accelerations, and it determines the distance. So if the front car is parked and the rear car is traveling, the d mean is must be very large. So in any case, what you described, the human intention, human expectation that the front car will move while it doesn't, that's not relevant here. No matter what your human expectation is, all these parameters are hard objective parameters that can be determined by the AV sensors.
Yeah, sure. So it's kind of correct, but it's a little bit inefficient. You know, if there's a long queue, it will take time before you start, and the human drivers behind you maybe are stressed or something. So in a way, you caused an accident by being too careful.
So whatever the accident, so maybe the human behind me is impatient and hits me because I'm stopped for too long, then it's his responsibility.
Yeah, sure.
Yeah, in the court of law.
Yeah, but actually, yeah, that's right. So, but it's difficult with the practice, so to say. And of course, humans will learn, oh, this is an autonomous car, it's very slow, so I have to wait or something. But in human situation where you kind of, yeah, don't follow the rules exactly,
No, but for
be
an
more
AV,
effective.
for an AV, if the front car, if the traffic light turns green and front car starts moving, then the D-min will be very small because the ego vehicle is parked. So if you do the formula, it's very small, so it can start moving immediately. It doesn't have to wait. Yeah, still the rule still applies. It's not a conservative rule. It's a rule that tries to ensure normal driving.
Yep.
Okay, any other questions?
Many of the situations here might have been avoided if the cars could talk to each other. I worked with the Prometheus project in 1980s, where we tried to have cars that communicated with each other.
Yeah, V2V communication is compatible with this.
Okay.
So V2V essentially helps you reduce the roll, reduce the reaction time.
Yeah.
So maybe the front car can inform the rear car that I'm about to slow down, and you can be prepared. So in any case, this formula describes physics, that is minimum distance to avoid collision given the velocities and acceleration parameters. So regardless of if they're V2V or not.
But if there are like car trains or something, when they drive very close to each other, if you have communication, then you need to violate those rules.
And also if the cars in the front have some danger in its path ahead, then it could tell the other car it's a possible situation.
Oh, yes, that could be V2V communication could be useful in this scenario, where, even though the yellow car cannot see the blue car with line of sight with radar, maybe the blue car will send a message from via V2V. So V2V is like a virtual sensor that allows you to sense non-line of sight. In that case, then the yellow car can set a proper D-min to avoid collision. Yes, it will be useful.
Okay.
So sorry that I took half an hour more. If you left earlier, that's fine, but it's all recorded. Any more questions?
Sorry, how could the exam? Sorry. If somebody else wants to walk, I want to talk. I will. Okay. How would the exam questions come from this section? Would we use these equations to derive an answer, or what exactly?
Yeah, the exam is open book and remote, so you do have access to your computer. So I may give you a few numbers, and you can plug in the formula to do the calculation for D-min. And also in the lectures, I had occasional quizzes, right? The quizzes are the type of questions that may appear in the exam.
Okay.
Yeah.
Thank you.
Okay, any more comments or questions?
I'm impressed by you being able to talk for like 4 hours. So I will only go for 2 hours next week and pre-record some stuff. So, and good with the students also to manage to listen concentrated all this time.
Thank you.
Yes, yes. It is a long afternoon. Yes. Okay, so for those who haven't submitted lab 1, you should finish and do it. As I said, it's a very simple assignment, so you should be able to finish even if you start now. Okay, so class dismissed.
Thanks. Bye.
Goodbye.
Thank you. Goodbye.